Hello, everyone. Thank you so much for joining us today. Hope everyone is doing well and staying safe out there. My name is Abby, and I am a project coordinator at 2H Offshore. With many industry events and conferences cancelled due to COVID 19, we've put together this series of live webinars to keep our valued clients and colleagues up to date on the latest happenings in the world of riser and conductor engineering. I want to welcome
Uh,
you all to our webinar today entitled Benefits of Composite Flexible Pipes in Offshore Applications. Before we get started, I would like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon, so please look out for a link in your email. Secondly, if you have technical or content related questions today, please feel free to ask them at any time. You can use a Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we will go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. And with that, I am very happy to introduce our speaker today, Nitin Rappel. Nitin has over 10 years of experience working on flexible pipe projects ranging from concept design through to manufacturing and integrity management. He is currently working as a principal engineer at 2H Offshore in Perth. He is responsible for leading the engineering and business development of flexible riser systems in Australia. Nitin graduated with a degree in mechanical engineering before pursuing his PhD at the University of Western Australia. He has previously authored and presented papers at numerous conferences and is a regular speaker at industry events in the Asia Pacific region. And with that, I will pass things over to Nitin to get us started.
Thanks, Abby, for the warm introduction, and thanks everyone for joining this presentation. Good morning and good afternoon, depending on where you are from. And let me get started with this presentation. I have briefly outlined my presentation in the slide. I'll be talking about the overview of composite pipe historically in oil and gas industry and how there is a new renewed interest of composite technology within the industry of late. I'll also touch upon the traditional flexible pipe and discuss the challenges that are resulting in use of more composite technology for flexible pipe systems. I'll also touch base upon two variations of composite technology within the flexible pipes, which is a fully polymer-based technology that's thermocomposite pipes, and also a variation of traditional flexible pipe with composites called hybrid flexible pipes. And then I'll talk briefly about how the new technology is enabling to address some of the challenging issues, such as the presence of supercritical carbon dioxide in the reservoir and annulus conditions of the flexibles, and also to help maintain the integrity of the pipe. And finally, there's some time for question and answers based on my presentation, and I would be happy to answer some of your questions. Let's get started. Historically, composite pipe has been used in oil and gas industry, but primarily for tubular structures and downhole components and ancillary equipments such as caissons and J-tube applications. However, there's a renewed interest for composite flexible pipe in the recent past, and this is owing to the renewed due to the recent developments in technology enabling the composite pipe to deliver on par with flexible pipe. And not only that, it is fully getting qualified for more harsher environments and critical applications. There are two noteworthy variations of composite pipes, which is a fully polymer-based technology, of which the key suppliers currently are Airborne Oil and Gas and Magma Global. But there's also a variation of use of this composite technology in the traditional flexible pipe segments, and the key suppliers for these type of variation are Baker Hughes and Technip FMC. It's also noteworthy that as the industry is progressing towards more harsher environments and ultra deep water fields, the acceleration of use of composite technology is increasing as well. So next, I venture into brief introduction of traditional flexible pipe and how the composite pipes can overcome the challenges based on the traditional flexible pipe. A conventional flexible pipe contains about different unbonded layers ranging from 4 to 19 layers, which each has a specific purpose to provide the integrity for the flexible pipe. Flexible pipe has been used in the industry for the last 30 odd years and has a very successful track record of delivering in offshore applications. The key components that provide the strength for flexible pipe are your carbon steel layers, which provide the load bearing capacity to the pipe. These carbon steel pipes are the heaviest components in a traditional flexible pipe, like the pressure armor, which provides the resistance against hoop stresses, is about 30 to 35% of the weight of the total structure. And similarly, the tensile armor layers, which provide the axial strength, are about 40 to 45% of the weight of the full structure. This additional weight affects and has implications on fabrication, transportation, installation, and operation. Further, the carbon steel is also susceptible to corrosion when exposed to permeated gases, causing integrity issues. It's also interesting to note that while these carbon steel structures provide the required strength, there's different variations possible for these carbon layers to suit the required field conditions. And more the harsher environment, you need a grade of steel which can accommodate the permeated gases. But unfortunately, these leads to a thicker grade of material, and this causes additional weight onto the pipe structure, which is also a disadvantage, especially if you're looking for deep water applications. So there's a need for an alternate material, an alternate technology, which could deliver the same level of performance, but it's also lighter and also promises a better integrity solution than the traditional flexible pipe. And hence, looking at different possible options, composite technology is one such option which provides the necessary requirements for industry to advance to the next level. What is composite technology? Composite materials typically mean a combination of two or more constituents in a heterogeneous combination, such that you exhibit a superior property than the individual constituents. Composite materials can be broadly classified as particle reinforced and fiber reinforced. Particle reinforced meaning particle getting embedded into a matrix. A good example of that is plywood that we regularly use in our day-to-day life. Ceramics is another good example. And the other one is fiber reinforced, where the strands of fiber are embedded into some kind of a host matrix. In our application, it would be a polymer. So it's a fiber embedded into a polymer matrix. And these fibers can be aligned in different directions to provide strengths in whichever direction that we want. For example, if we need more strength in axial directions, we can get that by varying the inclination of your fibers. And on vice versa, if we also need more strength against the pressure, so we can also change the orientation of these fibers to get more strength against pressure. So composite technology gives us more control on the manufacturing process, helping us to streamline the technology to suit the required field conditions. Now, there's been early adoption of composites in the oil and gas industry. However, the uptake was quite slow, primarily because of the economy of scale. Like, for example, it was a challenge to manufacture a long length of composite pipe initially, and that could never give us the economy of scale. But the recent advancements, especially in thermoplastics, has enabled to overcome such limitations, and there's a renewed interest for composite pipes for offshore pipe applications. Primarily, we can classify the composite pipes into two categories, which is reinforced thermoplastic pipes, where the composite layers are loosely bonded on top of the liner and then held on with a jacket structure. So this is not a bonded structure, but because the composite layers are loosely wrapped around the liner, so the pressure rating for such pipes is quite low, and hence the reinforced thermoplastics are primarily used in land-based applications. Thermocomposites or TCP pipes is another variation where the composite, the liner, and a protective layer, if you want, can be fused together and increase the resistance and strength of the structure. So this enables us to perform in a more challenging environment. So the thermoplastic composite pipe structure itself can be classified into a three-layer structure. Liner being the fluid tight conduit that provides uh, a fluid tight interface where you don't leak your reservoir fluids when it enters into the pipe and it is delivered to the required destination. It's extruded from polymers such as polyethylene, PA12, PVDF, and PEEK. All of these are well known for traditional flexible pipe. And then we have composite layer. Composite layer provides the strength, stiffness, and integrity for the pipe itself. Without this, it would be just a polymer structure, and it wouldn't have the necessary strength to deliver in challenging environments. And the composite layer itself consists of a fiber embedded into a polymer matrix, and the known combinations are glass and polyethylene, glass fibers and polyethylene, carbon fibers with PA12, carbon fibers with PVDF, and carbon fibers with PEEK. So we got three different variations of the layers. And the very last layer is your protective layer, where the protective layer provides you the provides necessary strength against any wear and tear, especially seen through the transportation and installation phase, and even the operations such as dropped objects. And it is the same material as your liner. Two key suppliers providing TCP pipes currently in this market is Airborne and Magma. Airborne takes the approach of fit for purpose polymer, enabling you to choose different polymers based on the need of the field. And what happens is we have a liner material, we have a composite material, and we have a protective layer, and all of these are melt fused to provide the required strength, forming a single laminate as a solid wall, giving you the strength for the application. On the other hand, we have Magma, which utilizes combination of PEEK and carbon fibers to deliver a very robust structure, and this is laser cured to form a single bonded structure. And selection of this material depends on various parameters. We have a matrix down below where we have performance against different parameters, such as, for example, temperature. Polyethylene has a very low tolerance. It's qualified up to 65 degrees. PA12 is qualified up to 80 degrees. PVDF can go as far as 121 degrees for TCPs. And PEEK can provide higher performance in excess of 130 degrees. And so on with your chemical resistance. So your polyethylene has the lowest resistance for various oil and gas chemicals that are regularly used, and ranging all the way to PEEK, which has a very high resistance. And similar with your mechanical properties as well. However, there's also a price line attached to the superior performance, and hence you'll see that polyethylene has a very low price to procure compared to a PEEK material. So what does TCP offer in terms of value proposition? So TCP pipes are lightweight, as it is a fully polymer solution compared to a traditional flexible pipe. It's light in nature, enabling you to manufacture more product and also result in use of less ancillaries in operation. It's corrosion resistant, again, a full polymer solution, no steel structures. Excellent fatigue performance. It's lightweight and not prone to corrosion, enables it to perform for a longer time and in harsher environments. It's collapse resistant, and it also has pressure rating equivalent to a traditional pipe. And this again goes back to the technology itself, where you can have multiple strands, multiple layers of polymer composite layers, so that you can increase or decrease the thickness, you can increase or decrease the alignment of the fibers to get the required strength. TCP pipes are smooth bore, which means lower pressure losses across the length of the flow line, or riser, which means you can get a same level of delivery of the content with a smaller ID pipe. And variation of the layers is also possible to suit the requirement. I mentioned that the traditional TCP is lightweight, but if you want to make it heavy, there's a possibility to use a weight coating layer on top of your protective layer to give the required strength. But if you're using a very high resistant material such as PEEK, so you can get away just using a liner and a composite material, which also provides equally strong properties and high resistance against wear. But there's also challenges associated with this. While lightweight is an advantage at one stage, it could also be a bit of challenge in another scenarios, especially in shallow water conditions, where on-bottom stability cannot be achieved easily. You might have to either use a weight coating layer, or you have mattresses to provide that stability. And also it's more susceptible to waves and currents, so which is not desired for flow line application or riser application. We have large MBRs for TCPs compared to a traditional flexible pipe. That's because of the composite nature of the composite layer, where these alignment of different fibers within the polymer is quite critical. And if you provide any compressive strength, there's a chance that these fiber structures can dislocate themselves from the polymer structure and can cause integrity issues. And also because of the thickness of the structure, the composite layer has a higher stiffness compared to a normal polymer. So this results in a large MBR. Insulation is limited. Unlike a traditional flexible structure where you can add on extra insulation layers, because the composite pipes are fuse melted or laser cured, it is a solid wall in essence. So there's a limited scope for adding any insulation within these structures. And it also has lower terminal velocity, which means the installation could be a bit of challenge. You may have to look at additional apparatus to help in installation. So to address the limitations of your TCPs while still retaining the benefits of TCPs, we have a hybrid flexible pipe. And hybrid flexible pipes is pretty much a novel approach of combining a traditional flexible pipe and the composite layer together to give you the required properties. So there's two variations where we can target the hybrid flexible pipe. One is to replace the pressure armor with a composite layer, because we have seen that the composite layer can also give you the same strength capacity as a traditional carbon steel structure. Or it's also possible that we could eliminate the first three layers of a traditional pipe, namely your carcass, your pressure sheath and your pressure armor and replace with a composite structure. So what happens is by eliminating part of steel, we reduce the weight and we can achieve a weight reduction in the range of 30 to 60% with these hybrid flexible structures. And also, it provides better corrosion resistance against some of the reservoir gases. And it provides a good balance between your traditional flexible pipe and TCP structures. Key manufacturers in this segment is Baker Hughes, who propose elimination of pressure armor and replace with a composite layer, and the pressure sheath is bonded to the composite layer. On the other hand, Technip has chosen Magma as their preferred supplier for the second variation of the hybrid composite pipe. So what we have is elimination of pressure armor, your pressure sheath, and carcass layer, and it's replaced with the M pipe that Magma has already excelled in. And then we have a set of design guidelines to streamline the functionality of your composite pipe and the hybrid flexible pipe. So there was a GIP led by DNV early 2015, which looked through the existing knowledge and guidelines of the industry. And as a result of this GIP, there was a recommended practice, which now has been formalized as a standard a couple of years ago. And it provides guidelines for qualifying the composite layer and the use of the composite technology in flexible pipes. So ranging from your small scale testing, mid scale testing, and full scale testing. So briefly, to look at how we can classify the whole gambit of flexible pipes, we have flexible pipe at the top and can be broadly classified into metal-based and composite-based. Metal-based pipes can be further classified as bonded and unbonded, and we got API 17K providing guidelines for bonded pipe, and we have API 17J providing guidelines for unbonded traditional flexible pipe. On the composite side of things, we have DNV GL ST F119 providing guidelines for composite material, and then for hybrid flexible pipe, we have 17B Annex H, which provides the guidelines to qualify the composite pressure and tensile armors. We also have other codes such as DNV GL RP 8203, which provides qualifications of new technology, and DNV US C501, which provides guidelines for composite components. It's also worth noting that API 17B Annex H refers to DNV US C501 for some of the qualifications. Next, I'll venture into defining what SCCO2 failure mode is and how it can be overcome by the use of composite technology. CO2, like any other flue gases, is also present in reservoir, and CO2 has this peculiar property of becoming supercritical at temperatures above 31 degrees and pressure at 73 bar. So the supercritical nature of the fluid means it behaves as an average of gas and liquid. And a good example is like it wants to expand as gas, but with the density of a liquid. What it does is it provides a very harsh environment for the carbon steel structures within the flexible pipe to function. And CO2 in its supercritical stage enhances the embrittlement of carbon steel by stress corrosion cracking mechanism. And failure of one or two of these wires would make the pressure sheet creep into the annular space, resulting into the small ruptures. And once these ruptures are evident, you see more hydrocarbons flowing into the annulus, and with with the reservoir fluids directly penetrating into the annulus, you'll see more and more accelerated corrosion due to the presence of other impurities such as oxygen and hydrogen sulfide and water. And eventually, when there's more pressure that the annular structure can sustain, you will have breach of your outer sheath and resulting in loss of hydrocarbons to the environment. A good example is Petrobras having to suffer a couple of incidents in the recent past continuously, and that's been attributed to the presence of supercritical CO2. And this is a mechanism which the industry is still trying to understand better and try to understand how the carbon steel structures react to this kind of environment. And we'll see that as the industry progresses more and more into harsher environments, even within this region, I can say that some of the fields such as Prelude or upcoming fields such as Browse or Ichthys, they are all high pressure fields with very high temperature requirements and very high content of CO2. So there's a proper understanding that needs to go on with the effect of how the failure mechanism of SeCO2 happens for these carbon steel structures. But let's try to see how a composite layer can provide an alternative approach to mitigate this problem. So thermocomposite plastics are fully polymer-based technologies, so there's no corrosion, and they are very lightweight, implies there's very little static load and provide you a better fatigue performance. On the hybrid side of things, again, we are completely replacing a carbon steel layer with a composite layer, which means we reduce the weight of the pipe and also reduce the permeation, because composite pipes have a better composite layers deliver a better performance against gas permeation compared to a traditional polymer structure, and will provide you a better strength by minimizing the rate of corrosion. So with this in mind, so we can definitely to some extent mitigate the corrosion aspect completely, or in a hybrid case, we can definitely reduce the nature of corrosion and hence make sure that we reach the required field life for the desired application. But there's also challenges with the presence of SeCO2 for composites itself. There's been numerous literature outside oil and gas where people have studied extensively the presence of and interaction of polymers with supercritical CO2. What presence of supercritical CO2 does is it influences even the mechanical properties of the polymers. It reduces the yield strength. It reduces the, or it accelerates the elongation of the polymer, and it affects the modulus of elasticity. Further, some of the CO2 could also be embedded within the polymer structure itself, but due to the nature of its movement back and forth, it could leach away some of the additional constituents that we add for deplasticizing the polymer, which means it could result in failure modes by thinning of your polymer and losing strength of your polymer. So this is something that the industry still needs to look into if we are using composite pipes to venture into an environment which faces supercritical CO2. In summary, what we have seen here is composite pipes are definitely gaining more prominence thanks to the thermoplastic technology getting more and more frequently used and updated with better qualifications. We see that composite material is trying to address the challenging environments such as supercritical CO2 and also help in weight reduction for dynamic risers for deep and ultra deep water applications. Design guidelines are more formalized and standardized now, and as industry operates more and more, we'll update these theoretical design calculations and practical use of composites in the field conditions. Um, and right now, where the industry is we have seen a lot of static applications for water injection lines and hydrocarbons, but the suppliers are qualifying the pipe for riser applications, and we'll probably be seeing a full-scale riser application in about a year and a half to 3 to 4 years time. And as this happens, we'll have better presence of TCPs within the flexible pipe segment. Something that I haven't touched base much in my presentation is TCPs and the composite technology itself could be an alternative for rigid pipe as well. A good example that I can think of is the Thunderbird semi-sub used in Gulf of Mexico. It's been beefed up to support the rigid pipes for the deep water applications, and it has put a tremendous strain on the need for more material and higher strength for that component. And looking back at the technology available now and use of some of these novel approaches, um, concept design would have been completely different. And this is to also lead to a point that if the composite technology was much more mature, say even 2 or 3 decades ago, we would have seen a completely different approach. I believe that the industry is heading in the right direction, and we'll see more and more applications of composites in the flexible pipe segment. I just want to introduce part two of this presentation, where a colleague of mine is going to talk about how the composite pipes are designed to overcome challenges for deep water applications in another 2 weeks' time. So that's on August 26th, 2020. And I would invite all the attendees to also register for the upcoming webinar. With that, I close my presentation, and I'm happy to take questions from you. Thank you.
Great, thank you so much, Nitin. We've already got some questions coming in from our audience, so I'll go ahead and get started. Have the TCP hybrid flexible pipes been used in the oil and gas industry before, or are they still under qualifications?
Yes, so TCPs have been in use, but as I mentioned, they're like the industry, and it's always good that we take a staircase approach, that we qualify the material at first and pass on this for lower demanding applications such as water injection lines, and then we ramp up for hydrocarbons and slowly get on to a fully dynamic risers. And with that in mind, I think the TCPs and hybrid pipes have been used for water injection lines and static flow lines in the past, but I believe the dynamic riser application is still in progress. So once it's fully qualified, we'll also see TCPs and hybrid pipes in dynamic riser applications.
Okay, thank you. Another one that's coming in is, are you able to give examples of how composite pipe has been used offshore to date?
Yes, so offshore to date, again, going back to my answer for my first question, the composite pipe itself has been used in some of the precoms and some of the water injection lines. And static applications, we have hybrid flexible pipes. I believe Airborne has successfully delivered pipes for Chevron, and there's also a case where it has delivered to Petronas in Asia Pacific region. So this is all static application at the moment, but I'm sure in a very short time span, we'll also see these pipes being used for riser applications.
Okay, thank you. Can we use a cheaper material like PE for the protective layer of TCP while using PDVF or PEEK for inner layers?
Um, so, as I mentioned, TCPs are melt fused or laser curated structures. And one of the chief criteria there is the interface between the different layers. And for that to have a very strong bonding, we need to have a similar material for all the three layers that we use, because the heterogeneous nature of the composites itself means that, with a with certain criteria, you could see that the fibers could dislocate themselves from the polymer matrix, and the interface between different layers could have a challenging applications if they're not properly selected. And hence, to have a proper bonding, we need to have a similar material for all three layers.
Okay, thank you. How does erosion affect the TCP's performance compared to traditional flexible pipe?
Um, um, Yeah, that's a good question. And I believe there's no straight answer. Like how we use currently for a traditional flexible pipe, we still need to qualify the pipe structure for erosion. And the good thing is, you know, we have a lot of variations of the pipe. So if we see at a point where your polymer is eroding faster and it's not qualified, we still have a variation like what Baker Hughes is proposing, where you can still have your carcass within the composite hybrid flexible pipe, and which can provide the same level of strength against erosion that you would get for a traditional flexible pipe. But given the context, I believe peak with the carbon fiber combination is is more geared towards giving better performance for any mechanical wear and tear, and hence it will also give a better performance against all other materials for erosion within TCPs.
Okay, thank you. What is the largest ID possible for TCPs?
Um, it's an interesting question because even for traditional flexible pipe, we say probably 18 inches or 19 inches is the limitation. And I believe from technology point of view, there's no limitation. Once we get the technology qualified, I think it's the manufacturing limitation that actually sets a limit on the structure that we can manufacture. And right now, the hybrid flexibles or TCPs, I'm looking towards 6-inch to 8-inch ID range, and that's because of the immediate use of that ID, especially for the deep water applications. But I believe if there's a stage where the technology is more mature and people and operators start accepting these for larger pipe applications, we could also see um, the composite pipes for larger ID pipes such as 12-inch.
Okay, thank you. Why does peak carbon fiber composite perform better in restriction permeation of CO2?
Okay. Um, I think it's got to do with the molecular arrangement of the different compounds within the material itself. And again, there's a fair bit of literature available where the fiber materials, when it gets embedded into the composite matrix, how best it aligns itself at a molecular level with the um, host material, which is the polymer material. And I think the best fit happens for carbon fibers and peak materials. And with that, the molecular gap that actually causes here permeation is very less with peak and carbon fiber combination, and which translates into a less permeation. I believe it's in the order of 50 to 100 times less compared to um, traditional PVDF.
Okay, thank you, Nitin, for all the information on the topic. That is all the time we have for today, but as we have mentioned earlier, if we didn't get to your question or if you would like to continue this discussion, please contact Nitin directly using the details provided here. Thank you to our audience for your time and participation. We hope you all found this useful and will join us for more webinars in this series happening every 2 weeks during our time at home. Check out the 2H website for more details and to sign up. Again, please look out for the recording of the webinar in your email in the next 24 hours, and we hope you enjoy the rest of your day.
Thank you.